let's introduce the concept of a phasor, and this is going to be a powerful method to represent sinusoids. What a phasor is a complex number that's going to represent both the amplitude and the phase of the sinusoid as we defined previously. So let me go ahead and write this down, and now you'll see why we need to talk about complex numbers. So a phasor is a complex number that represents the amplitude and phase of a sinusoid. So essentially the key here is it's a complex number. So to do that, to understand phasors better, let's do a quick review of what a complex number is. So if we define this in rectangular form, so let's go ahead and define in rectangular form the complex number. It can be written as z equals x plus, or I'll say j y, where j is going to be equal to the square root of minus 1. Here x is going to be, so we get the real part, so this is going to be the real part, and then of z, and then y is going to be, or the imaginary part is going to be y. So the imaginary and then we can see this in the graph here in a second. So this is rectangular form. We could also define this in polar or exponential form. So we can define it in polar form, which is going to be z equals r, the angle phi, or exponential form, which is z equals r e to the j phi. So these are all the same thing, just different formatting. Alright, so why is this important? Because this can simplify our analysis of sinusoidals or sinusoid functions, and also help us with simplification of the math as well. So let's go ahead and define this guy here. Look at the chart here. We have r defined here, we have our angle defined here. This is going to be our real axis, this is going to be our imaginary axis. So this is going to be the representation of our complex number here. I was going to rewrite it, so z equals x plus jy, which is r angle phi. So we'll be using this format for AC circuit analyses. So remember the real and one thing, don't confuse this real axis and imaginary axis with the cosine and sine figure or axis we presented in the previous lecture. So given these three different formats, we can define a couple more things. We can define our r and our phi here. So r is going to be square root of x squared plus y squared. And then similarly, phi is going to be tangent inverse y over x. Okay, so if we know r and phi, we can obtain x and y. So we can go between these two, between the two different coordinate systems. We know x is equal to r cosine phi, and y equals r sine phi. So we can keep these as additional definitions here. Okay, so I can further simplify this or rewrite this as z equals x plus j y, which is equal to r angle phi, which is equal to r cosine phi plus j sine phi. Okay, so this is another way of writing this relationship here. Okay, using this here. So we can go from the rectangular form or go to the polar form and go back and forth between them as we like. Okay, and there's of course some different properties, operations that we can do with complex numbers. We can do addition, we can do subtraction, multiplication, division, and we can go ahead and define them here again, since this is a review before we do some examples. So for addition, we can say z1 plus z2 is going to equal to x1 plus x2 plus j y1 plus y2. For subtraction, z1 minus z2 is equal to x, and these are just mathematical operations for complex numbers that are good to know when we're doing our analysis. x1 minus x2 plus j y1 minus y2. Scroll up a little bit. If we do multiplication, z1 times z2, that's going to be r1 r2, the angle of phi 1 plus, or phi 1 by 2. Division is going to be z1 over z2. It's going to be r1 over r2, angle phi 1 minus phi 2. Reciprocal, so if I say 1 over z is going to equal to 1 over r, angle minus phi. Square root of z is going to equal to the square root of r, angle phi over 2. And then the complex conjugate is going to equal to x minus j y, which is r angle minus phi, which is equal to r e to the minus j phi, or phi. Okay. So this is just a quick review of some of the operators and things you can do with complex numbers. Okay, just a couple of the things you can do with them as a review. Okay, so now that we've gotten that out of the way, we can talk about phasors. Okay, we can talk about phasors. In phasors, when we talk about them, we want to put them, represent them using Euler's identity. So when we talk about phasors, we're talking about Euler's identity. Okay, and essentially what that says is e to the plus or minus j phi is equal to cosine phi plus or minus j sine phi. Okay, just some additional definitions. And from this we can represent the sinusoid as a real component of a vector in a complex plane. Okay, so we can say, we can break this down into our real or imaginary, where again our cosine here is going to be our real component, and then this is going to be our imaginary component. So we can say cosine phi is equal to RE e to the j phi, and sine phi is equal to Im e to the j phi. Okay, so that's going to be both our real and imaginary components. Okay, so the real part and our imaginary part. So now if we go back to the voltage that we were using, let's just say we use a voltage with a cosine, so sinusoidal voltage. Let's just say we have, let me move this down here. Move these down just a little bit more. Okay, so let's just say we have V of t is equal to Vm cosine omega t plus phi. We can rewrite this as V of t is going to equal to the real component Vm e to the j omega t plus phi. Okay, or V of t is equal to real component Vm e to the j phi e to the j omega t, and that will give us V of t is equal to the real part, some vector v e to the j omega t. Okay, and this vector is going to be in polar form. So this vector v in polar form is at an angle phi with respect to the positive real axis. Okay, and the length of the vector is going to be the amplitude of the sinusoid. Okay, so here we can further define our phasor. So if we look at this figure here, let me bring this back up. Look at this figure. We got v of t is a real component, the vector in polar form e to the j wt. Alright. And phasors are going to typically be represented at t equals 0. And they can be graphically shown in this figure here. Okay. And what does this figure do? So we have on the left side, this is what we call a sinor, rotating counterclockwise. Okay, it's going counterclockwise, and here it's going to be the projection of that sinor as a function of time on the real axis. Okay. So at t equals 0, this is what that value is, or excuse me, t equals t naught there. And then of course as you go up and down here, the angle is going to change, go up and down, and you rotate based on this angle, and you can do the projection of the sinor there. And we can define a transformation between time domain and this phasor domain. So we got, in this case, this is our time domain, this is our phase. You can say v of t is equal to Vm cosine omega t plus phi. We can go back and forth between that and v, which is just v m angle phi. Okay. Where this is going to be a vector. And this is essentially what the phasor is. Here, this is going to be our time domain representation, and this is going to be our phasor domain representation. Okay, so we actually have a summary table here between these two. So we have our sinusoid phasor transformation. So you can go from time domain to phasor domain, where if you have a cosine, it's going to be represented that way. You have our sine with some for the voltage, it's going to be this way, and then you can do the same thing for the current source. This is the way it's going to be represented, and then whether it's a cosine or sine. Okay, so we have a sinusoid phasor transformation relationship that helps us transform time domain to phasor domain. Okay, so what does that really mean? And essentially that's going to give us, when we're going from time to phasor domain, really essentially what we're doing is we're going from time to frequency domain. So sometimes you see that as frequency domain. Okay, so the phasor domain is also going to be related to or named as a frequency domain. Okay. So we can do a couple more things here. We can apply derivative to the phasor, and you're going to get, so let's just say if we have dv dt in time domain, we can go back and forth. That's going to give us j omega v in phasor domain. And so this is if we apply derivative. If we apply an integral, to a phasor, we get v dt. This is our time domain here. Go back and forth. And that's going to give us v over j omega, and this is our phasor domain. Okay. And then note these guys. This is a vector, this is a vector here. So there are some differences between this v in the time domain and then the v, the vector and phasor domain. Okay, so in the time domain, this is going to be instantaneous in the time domain, while the v is the frequency or the phasor domain. Okay. V of t in the time domain is going to be time dependent, while this big V is not. And then V of t in the time domain is always real with no complex terms, while V is going to be generally complex. So just a couple things to consider as you move forward with analyses in this circuit analysis, AC circuit analysis. Okay, so that's a quick introduction to phasors using complex numbers. Hopefully should be a review of these complex numbers. And then the concept of phasor and being able to go back and forth between phase and time domain, or frequency in time domain. And that's going to help us in our setting up our analyses in the next section.